Okay, this is the 10th section of the flipped classroom. Today we're going to talk about continuity of a function. What is continuity? Well, a function can be thought of as continuous if there's no breaks or gaps when you look at a graph of the function. A subjective way to look at this is to ask if you could draw the function with a graph without removing the tip of your pencil from the paper, then that function would be continuous over the interval that you drew it. Okay, for example, if you graph the height of a flower over time, the graph would be continuous because there would be no time where the height would be undefined or non-existent. The test for continuity is simple. We would say that a function is continuous at c, x equals c, if it meets these three conditions. F of x is defined at c. The limit exists at x equals c, and the limit of f of x as x approaches c equals f of c. We would say this function is continuous over the interval if it meets these conditions for every point c in the interval. Okay? So those three conditions, if either one of them fail, then the function would not be continuous at that point. We would say it would be discontinuous. Here's an example. This function, the square root of 4 minus x squared. The domain of the function is -2 to 2 inclusive. If you graph it, which I've done here, I've sketched a graph on the right-hand side, you can see that it's continuous at every point in its domain. There are no gaps. We would say that this function is continuous over -2 to 2, including those points. Not all functions are continuous. If you can see the first function, and I see that this is a bit hazy, but the first function is just a straight line. That function is continuous. The second function, where the function is not defined at the same point of the previous one, would be discontinuous at that point. And the third function, even though the function is defined, okay, as indicated by this dot, and the limit does exist, we would say the function is not continuous or discontinuous because the limit, although it exists, the limit does not equal the function value. Okay, it's interesting to note that in functions b and c, or graphs b and c, the reason that b fails is because the function is not defined. Okay, the limit does exist. We could remove this discontinuity simply by defining the function at x equals 0. In C, we could also remove the discontinuity because all we have to do is define the function or redefine it at x equals 0. So if we redefined it as, say, 1, then the function would be continuous. The limits, in order to remove a discontinuity, the limits must exist, and we just change the definition of the function. Okay? We'll show you an example here where you can't remove it on the next slide. Okay, if you look at the first function, step function, you can see that this one fails for the reason of the limit not existing. Obviously, as we approach the function at x equals 0 from both sides, we get two different limits. The limit does not exist. Therefore, this limit cannot be removed, or this discontinuity cannot be removed. Okay, we can't just, by redefining the function, make the limit exist. It's also interesting to note, if you look at the right-hand drawing, we could talk about a left-hand discontinuity, a left-hand continuity at x equals 0. In other words, we would say, does the limit exist as x approaches from the right? Well, yes, it does. And does the function, is it defined as we approach from the right? Yeah. And is the function value the same as the limit as we approach from the right? Yeah, it is. So we would say that this function has a one-sided continuity. The middle function here, which is 1 over x squared, I wrote that in there just so that you would know, we would say is discontinuous at x equals 0 because it's an infinite discontinuity. In other words, there is no real value that x approaches, the function approaches as x approaches 0. This discontinuity cannot be removed because the limit does not exist. The last one is y equals sine of 1 over x. Okay, this is called an oscillating function. The values bounce as you get close to 0. The values tend to bounce between 1 and -1. And it's really hard to tell where the function value is because it just bounces back and forth. We would say that the limit does not exist here, therefore it has a discontinuity and it's non-removable. Some properties of continuous functions. Well, the same properties we discussed for limits of functions basically apply to continuous function. So if f and g are two continuous functions at x equals c, then the sum of those two functions would also be continuous at x equals c. Or if f and g are continuous at x equals c, then the product, or the quotient for that matter, would also be continuous at x equals c. And the last little property that we're going to talk about is continuity of composite functions. If f and g are continuous at x equals c, then their composite f of g of x would be continuous at c, or g of f of x also would be continuous at c. Sometimes that's a useful thing to know. So it makes sense that if you have two functions that are continuous individually and you put them together, making one the inside and one the outside, then their composite would also be continuous. The next slide is your practice problems. Excuse me. And we'll see you in class. Thank you.